In this example, we have a steel string holding up a 2-kilogram mass. And the question we want to answer is how much will the steel wire stretch under the load of the 2-kilogram mass? So it's going to have some change from its equilibrium length, delta x. The things we know about this wire are that it has a diameter of 0.60 millimeters and a length of 1.1 meters before it gets stretched. Now, if I don't know anything about this problem, I hopefully remember that Hooke's law describes how stretchy things work. So I'm looking for some equation that looks like Hooke's law. And sometimes there's a negative here to indicate that the force pulls against the change in position. If I'm just worried about the magnitude of force, it's k delta x. Or you can put that negative here to remember that however you stretch the thing, it will want to pull the opposite direction. But this steel wire, I don't know the spring constant for. However, I can find it if I know something called Young's modulus, usually represented by a y. Young's modulus, in general, describes how stretchy things are, or how hard to compress them. The way to get from Young's modulus to the spring constant is this equation. Spring constant equals Young's modulus times cross-sectional area divided by equilibrium length. This cross-sectional area, what it means is, if you imagine a wire being a very thin cylinder, then the cross-sectional area is if I took a very thin slice of this, what it would look like. And if I took a very thin slice of a cylinder, it would look like a circle. So the cross-sectional area is the area of the circle, or you could think of it as the area of an end of the wire, which is just pi r squared. I want to know how much this thing changes position. So once I've found k, I'll also need to know the force. Well, if I think about a free body diagram for this situation, there's gravity and there's tension. So I need to find the force of gravity on this block that's hanging here. And force of gravity is just mass times little g. And I like to, for approximation purposes, just call little g 10 newtons per kilogram. So the force of gravity on this block would be 2 kilograms times 10 newtons per kilogram. Now, if you're doing a WebAssign problem and you need to be really specific, you can use 9.8. That is a much better estimate than my 10. But it's really easy to use 10 because now I know that this is just 20, and I really didn't have to think much about that. So, in theory, I can find k, and I have f, so I should be able to find delta x. But let's turn that theory into reality. Let's figure out what k is. So k equals Young's modulus. Well, I'm not sure what that is. So if I go find a table or textbook that can tell me Young's modulus for steel, I'll be in business. And I looked this up in your textbook and found it in Chapter 9, Section 1, that Young's modulus for steel is 200 times 10 to the 9th newtons per meter squared. So that's my Young's modulus. The cross-sectional area we already discussed is pi r squared. Now I don't have r, but I do have diameter, and radius is just half of diameter. So this would be, my cross-sectional area is going to be pi 0.3 millimeters. This number of Young's modulus is given to me in meters, or with dealing with dimensions of meters anyway. So let's go ahead and just convert that to meters. 1 millimeter is 10 to the negative third meters, so that's easy. And that was my radius, so I have to square it. Divided by my equilibrium length, or the length before I stretched it. And that is 1.1 meters. And if I work this all out with the calculator, I get 5.14 times 10 to the 4th newtons per meter. Now I can find delta x. Delta x equals force over spring constant, just looking up here. Or if I really want to be specific, because we're having the force and the displacement go in opposite directions, oh, and by the way, this is important. So this force isn't directly just the force of gravity. I was a little sloppy there. So this force is the tension within the string, so how much that thing is pulling back. So really it's the tension force, but I just made a leap that I really should have explained here, that if this block is in equilibrium, so if it's not just falling straight down or flying up through the ceiling, then these two forces need to be equal because the block won't be accelerating. So I know Fg equals T, and so if you were wondering, wait, won't the thing stretch in the same direction as the force? It seems like that negative shouldn't be there. That's the reason. We're actually talking about the tension force. So the force pulls this way, and the string gets stretched a delta x down. So our delta x is going to be, if I start subbing in my numbers, 20 newtons over 5.14 times 10 to the 4th newtons per meter. I get that this thing stretches 0.389 times 10 to the negative 3rd meters, or 0.389 millimeters. And this, if I'm keeping track of my negative, should have come through. So that tells us that the block was stretched down because I was treating that force of tension as a positive.